Okay, good morning, everybody. Let's get started. Okay, we have our first exam next week.
Oh boy.
So we have three choices. We can have it on Monday, we can have it on Wednesday, or we can have it a take-home exam.
Take home.
Take home?
Is take home harder or easier?
Well, it'll be harder problems, but it'll
Not
probably
necessarily harder or easier. Might be harder for you because then if I give you 24 hours, you're going to keep busy 24 hours. Take home?
take home.
Any objection to take home exam? Objection? Once, twice, thrice? Okay, we'll have a take home exam next week.
When is it going to be due?
We'll see. So we'll either assign it on Monday and have you turn it in by Wednesday, or Wednesday, we'll see, depending on the exam, but either on Monday or Wednesday. And maybe on Wednesday, I'll let you know, like, when is it going to be exactly.
I have to start on Wednesday.
What is it?
I prefer to have it start on Wednesday.
I'll let you know on Wednesday whether it's going to be on Monday or Wednesday.
It's not going to be assigned until next week.
I mean, I know, I just, okay,
Good?
yeah.
Okay. So we're going to try to finish the sampling in this class, so we move on to the next topic. And what we've done in the previous class, any questions on the material in general? So in the previous class, we looked at the downsampling. What is the downsampling?
Reduce size.
If I have a signal that is sampled at a certain rate, and I want to reduce the size of that file, I can sample at a lower rate. So I'm going to take less samples. The question that we asked and we answered is by how much I can reduce the sampling rate and still have no aliasing. We said when we reduce the sampling rate, then the spectrum, when I plot it against omega, is going to get bigger. And therefore, we have to watch for the aliasing and the condition that we derived in order not to have aliasing. M has to be less than pi divided by omega b. Does that make sense, everybody? Okay. So what we're going to be looking at today is the upsampling. So what happens if we have a system that is designed to operate at a certain sampling frequency, however the signal that we have at the input is sampled at a lower rate, and therefore we want to increase the sampling rate of that signal. So this is what we're going to do. We're going to first look at what happens if we do interpolation formula in order to add samples to the signal, and then we're going to do the upsampling, and then we're going to relate the two together. Make sense? So it's going to be probably slightly confusing till we cover it all together, but then it will come together. So starting with properties of the discrete time Fourier transform, which we will study in more details later. And this property is the time frequency scaling. What this property says, if you have a signal, and we're going to have a subscript of n, that is equal to x of n divided by capital N, when n over capital N is an integer, and it is 0 elsewhere. Then the discrete time Fourier transform of this signal is going to equal to x of e to j omega multiplied by n. What does all this means? What this means is the following. If I have a signal and then I have an interpolation formula, that is obtained by setting missing data to 0. So what this says, if you have a signal x of n, so I'm going to put on both sides what this property says. If I have a signal x of n, and this x of n looks something like this. So this is a signal, and we sampled it to get x of n. Now what I've done with x of n comma n is I came to this signal that was like this. This is the signal. This is x of n. So these both are the same. However, what I did, I came to this signal and I added samples to it. And these samples have a 0 value. So I just added zeros to the signal. Does that make sense? So I have a file that has a value here of 15. The one after it is 10. What I did, I came and said, now it is 15, 0, 0, 0, and then 10. Make sense? Everybody? Yes, no? So if this is 0, 1, 2, 3, 4, and 5. So in this case, I have x of 5 of n is going to equal to x of n over 5 and 0 elsewhere. N over 5 is integer. Does that make sense? Everybody sees that? Nobody sees that? This is x of n. I created a new signal. I call it x sub 5 of n. What is x sub 5 of n? It's going to equal to x of n over 5. So when n is 0, this is x of 0, which is this value here. When x is equal to 5, it's going to be x of 5 over 5, which is x of 1. And this is x of 1. This is 0, 1, etc. etc. Make sense? Now between the 0 and the 5, it's going to equal to a 0. Elsewhere, it is a 0. Everybody understood this? Interpolation formula? So I kept the samples the way they are. Between them, I added zeros. I added 4 zeros, then we increase the n is equal to 5. Okay. So what this property tells me that we just listed above is that if you have if the spectrum of your original signal looked like this, and this is omega, and this is x of e to j omega, and this is omega 1, this is 2 pi, then the spectrum of this interpolated signal is going to look something like this. This is x of n e to j n multiplied by omega. And this is my omega. So this is going to have, if this was omega 1, it's going to be omega 1 over 5. This is going to be 2 pi over 5, and so on and so forth. The whole omega axis is going to be still pi n. So in this case, if it is a 5, n is equal to 5. In general, this is going to just equal to n. Does that make sense, everybody? Again, this follows directly from this property. If I interpolate or add the zeros between the samples of x of n, then the discrete time Fourier transform is going to become e to j omega multiplied by n. This is scaling of x of omega. Make sense? When I multiply it by n, what is going to happen to the axis? It's going to get divided by n. Is that clear? Everybody with me? Okay. So this is one thing. So what happens when I take a signal and just pad it with zeros? The spectrum of it is going to go from looking like this to looking like this. Why is that the case? This follows directly from the discrete time scaling property. You add zeros here, the spectrum is going to shrink by a factor of n. Okay, that's all good. Now what happens if I come to the signal and instead of padding it with zeros, I increase the sampling rate? So instead of sampling the signal every t second, I'm going to sample it. X of n is going to equal to x of n multiplied by t divided by n. What does that mean? Instead of sampling it every second, now I'm sampling it every second divided by n.
What's the subscript for the first x?
Upsampling, u. So what this means, if I have my x of n, if I sampled every t second, this is my original signal. This is every t seconds. Now, what I'm sampling it every t over n. This is 0, this is t, and now I'm taking samples every t over n. This is x of n, and this is upsampled of n. I increase the sampling rate. Instead of being every t second, now I'm sampling every t over n seconds. Okay. Now what I want to do, I want to look at how the spectrum of this signal looks like. So if I calculate x of e to j omega, similar to how we've done when we first plotted the spectrum of the sample signal, the only difference is instead of having a t as the sampling time, it is t over n. So x of e to j omega is going to equal to 1 over t over n, the summation from k equal negative infinity to infinity, the continuous signal j of omega minus k multiplied by omega s, and omega is equal to w divided by t over n. So when we've done it, when it was t, omega equal w is equal omega over t. Since we're using t over n, w is going to equal omega over t over n. Okay. We can write this as equal to n over t, the summation from k equal negative infinity to infinity, x continuous of j of omega over t over n, minus k multiplied by 2 pi divided by t over n. And therefore, we can write this as equal to n over t, the summation from k equal negative infinity to infinity, x continuous of j And we can write this as omega minus 2 pi multiplied by k divided by t divided by n. Together? And therefore, if I were to plot the discrete time Fourier transform of this signal, it's going to look something like this. This is n over t, and if the original signal has a bandwidth that is w, is going to get multiplied by t over n. This is omega, and this is 2 pi, negative 2 pi, and so on and so forth. This is x upper of omega, or of e to j omega. Together? So again, nothing new. If when we sample the signal, we calculate the discrete time Fourier transform. Here we just change the sampling rate, and instead of, since we have t over n, it's going to get multiplied by the spectrum of the signal. So this is going to, instead of this being wd multiplied by t, now it is wd multiplied by t divided by n. Okay. Now if I look at this spectrum that we just generated and look at the spectrum that we had before, the one we have in the page before, we realize that if I want to increase the sampling rate, I can do the following. I can take the signal that I had, x of n, I can expand it by n, and then I'm going to pass it through a low pass filter that has a gain of n multiplied by a low pass filter of omega. And this is a discrete time low pass filter, or a digital filter. And if I do that, I'm going to get x upper of n. What does all this mean?
Sampling is the same as
Okay, let's explain. So, my ultimate goal is to increase the sampling rate of the signal. I have a signal like this. I want to increase the sampling rate like this. One way I can increase the sampling rate, just sample at a higher rate. Make sense? Then I get a higher sampling rate. I'm done. The other option is to take this signal, pad it with zeros, and then pass it through a low pass filter. And if I've done that, I would get the same result as if I were sampling at higher rate. Again. So to increase the sampling rate, of the signal, we have two choices. A, sample at higher rate. Make sense? If I increase the sampling, I sample higher rate. The second option, which is we just introduced, is expand the signal and what that means, pad zeros between samples and then pass it through a low-pass filter. Both of these will give you a signal that is sampled at higher rate. Together? Is that clear?
I'm not sure if I quite understand how it goes from the expanded zeros to the
Excellent. Because we said when we expanded the signal, we get a spectrum that looks like this. We agree with this? When we expand it, we just added zeros. Now what I'm going to do to this signal, I'm going to come here, I'm going to pass this through a low-pass filter. So if I pass it through a low-pass filter, I'm only getting this part. If I'm getting only this part, this is no difference than what I have here. Does that make sense?
If you go back to that last page, so the reason, okay, because you're expanding with zeros in the time domain, it's shrinking the frequency.
That's correct.
There.
Yes.
That's right.
I'm passing this in the time domain, I'm adding the zeros. Then I'm passing it through a low-pass filter. It will average these, and instead of these being zeros, they will act as if they were samples between the two values.
Yep.
Make sense, everybody? So again, let's repeat it.
Why does pad have two Ds?
Sorry?
You wrote pad with two Ds.
I meant to say having, and then skip the ing. Okay. So again, let's repeat this one more time. So we're going to increase the sampling of the signal. We said we can just sample it at higher rate. That's an option. The second option, take the signal, pad it with zeros. When you pad the signal with zeros, the spectrum is going to look something like this. This comes from the discrete time Fourier properties. Then we say, pass this through a low-pass filter. If you pass it through a low-pass filter, then the spectrum that you're going to be getting is going to look something like this, which is no different than if you were to sample the signal at a higher rate. So therefore, another option is just to pad the signal with zeros and then pass the signal through a low-pass filter. Make sense?
So you're not adding information, you're just shrinking that window. I don't know. It's,
Well,
you can't fix the alias. Like this is, if it's alias, it's
no, there's no
Yeah,
aliasing. This
right.
all assumes there's no aliasing.
yeah. Okay.
Okay? And it all assumes we are obeying Nyquist theorem. Okay? In all this discussion, Nyquist theorem is obeyed. You can sample a signal. You can sample a signal. I have a signal, I sampled it. I've taken enough samples to be able to reconstruct it. However, I have to pass this signal to a system that expects a higher sampling rate. Does that make sense? So therefore, I cannot go back to the signal and sample it at higher rate. What I can do is I can come here, pad it with zeros, pass it through a low-pass filter, and the result will be samples that are added like this. Make sense? It would add these extra samples to the signal so the system can operate on this signal. And this is what the upsampling is going to do. Is that clear, everybody? Okay. And I probably have to write here, this is WB multiplied by T over M. Omega 1 is WB multiplied by T divided by M, which is the same here. WB multiplied by T divided by M. Okay. Any questions? Is the concept clear? At least? Okay. Now the last topic we're going to talk about I'm just going to copy these and paste them back to our lecture. Is quantization. What do we do with the quantization? I mean, so far, we've been looking at converting the signal from analog to digital. And so far, we've been just looking at what happens in the time domain, isn't it? How fast we're going to have to sample the signal, how the signal looks like in the frequency domain. However, to convert to a digital, what else we have to do? We have to look at the level. If we want to convert it to a digital, we have a finite set of values that we can assign to the amplitude of the signal. And therefore, this is what the quantization does. It's a nonlinear and non-invertible process which realizes the mapping. We're going to take the sample xs of nt, which is equal to x of n, and we're going to assign a value xk to it. Xk belongs to a finite set, which are the values that are allowed for the signal to take. Together? Why is this non-invertible?
You're losing data.
What else? Remember invertible property of a system? A system is invertible if I can look at the output and go back and get what the input is, isn't it? So for instance, if I have a system that is 5x and I tell you the system output was 10, you're going to tell me the input must have been 2. Make sense? If the system is x squared and I tell you the output is 25, what is the input? No, it could be negative 5. So therefore, it's not invertible. You tell me it's...
Okay.
I cannot go back from the output and know what the input was. And the same thing applies to quantization. When I quantize the amplitude, once it's quantized, I have no idea what the exact value that caused that gave me that level. Does that make sense?
Yeah.
And we'll see it. Hopefully you're familiar with it, but we'll see it. So what we're going to do with the quantization, we're going to have the signal amplitude range. We're going to divide it into L levels, IN, using L+1 decision levels, D1, D2 to DL+1. So what we're going to do, we're going to come to the signal level. We're going to divide it into intervals. So each one of these is interval. And then we're going to assign the value to the signal, depending on what the signal value is, where the signal value falls between these levels. We're going to assign it a quantization level. Does that make sense? So if the signal amplitude happens to be in this range, I'm going to assign it this quantized level. If it is in this range, I'm going to assign it this quantized level, and so on and so forth. Okay. Now, usually, we see the graph that relates the input, which is the signal level, to the quantized output, which looks like a staircase here. So this represents, the x-axis represents the input signal, the amplitude of the input signal, and the y-axis represents the quantization level. What does this mean? If the signal falls between See, I cannot do that on the board because people on the Zoom are not able to see it. If the signal falls between this value and this value, I'm going to give it a quantized level that is equal to this value. If the signal is between this value and this value, then the quantized level is this value. And once you quantize it, once I tell you this quantized level is 2 delta, I have no way of knowing whether The signal could have been anywhere between 3 delta over 2 and 5 delta over 2. I have no way to know what the exact value was.
Yeah, because you're rounding.
Because I'm taking all that range and I'm assigning it a single value. So the
Yes.
signal could have come from any of these values. Okay. So if you look here, in this example, how many levels we have? We have 8 levels. 1, 2, 3, 4, 5, 6, 7, 8 levels. And therefore, if I have the range of the input signal, this is the range of the input signal, I'm going to have the delta that is equal to the range divided by 2 to 3, which is the 8, which is equal to 0.125. So this represents my delta. Okay. Now, the step size or the resolution, as we said, is equal to R divided by 2 to the B, which is B is the number of bits that we use with the quantizer. So in the previous case, if it is 3, 2 to the 3 is equal to 8. And R is the range of the input of the signal. Okay. Now one thing we're going to mention, and let's look at the simplest of all these. All these are similar. All the levels are similar. However, we're going to look at the level when it is around the 0, just easier to see it. If I have a signal, the input of the signal is in this range, between negative delta over Q and delta over Q. Good? If the signal is 0, what is it I'm going to be assigned to it? A 0. If it is a slightly less than delta over 2, what am I going to assign to it? A 0. A slightly bigger than negative delta over 2?
0.
A 0. If the signal can have any value. Make sense? The signal can have any value. So if I have signals in this range, what is the error going to be equal? What is the range of the error that I'm going to generate by quantization? Delta over Q. Because the signal, worst case, I'm going to be almost at negative delta over 2. I'm going to assign it a 0. How much error I generated? Delta over 2. I could be at this level here, very close to delta over 2, the input. I'm assigning it a 0. How much I lost? A delta over 2. Does that make sense? So therefore, if I look at the distribution of the error, it's going to be in the range negative delta over 2 to a delta over 2. Make sense? Where is this coming from? Everybody? So when I'm here, when the input signal is here, I'm assigning it a 0. I'm generating an error that is a delta over 2. When I'm at the other extreme here, almost negative delta over 2, I'm still assigning it a 0. So the range of error that I'm creating is between delta over 2 to negative delta over 2.
Yeah.
And the same thing applies over all ranges. Why is this important? Is it important?
Yeah, you don't want it to sound like a robot if it's audio, so that's...
Yes, because when we are studying any system, and we realize there's a quantizer in the system, and I want to be able to study the performance of the system, I can take the signal and say, okay, I have a perfect quantization. In addition to that perfect quantization, I have an error signal that is in this range. Does that make sense?
Yeah.
So if I were to study the performance of any system, I can model this error as added to the signal. Let's say the quantizer is perfect. Whatever your signal is going to generate it. However, there's an error component, and this is the distribution of that error component. Does that make sense?
Yeah.
Everybody? Convinced? Yeah. Okay. Okay, so this is an example. And I have the code here, so you can, if you like, when you go home, you can run it and verify it So I have a sinusoidal signal that I want to quantize. And I have 8 levels that I can assign to these levels of the sinusoidal signal. How do I assign these levels? I can have this translation, the staircase, that is the translation between the signal level and between the quantized level. I come to the signal value. For instance, this signal value here, it's a 0. So I'm going to go here and say, okay, it's a 0. It is assigned a 0. I'm going to come to another signal level. Let's say this signal level here. I'm going to go here. It's going to be assigned this signal level. This signal going to be assigned this signal level. Make sense?
Yeah.
So this represents the range. So this range is all, any signal that is falls within this range is going to be assigned a 0. Any signal that falls within this range is going to be assigned this value. Any signal that is assigned within this range is going to be assigned the other value. Okay. So same thing, if I can make a straight line. So all these signals range is going to be assigned this value. Together? Now one thing also to keep in mind is that when we assign the output of the signal, we use the 2's complement to assign the value. And the 2's complement, x is equal to negative b0 plus the summation of b e multiplied by 2 to the negative l. So therefore, when we assign the levels in our example, the 0 is assigned a 0, then we assign a 1, a 2, a 3. This is going to be 2's complement, which is going to equal to 1 multiplied by negative.
That'd be negative 1.
Negative, what is the formula? Is going to, negative b0 plus, this is the b0 is the most significant bit. So 1, 1, 1 is going to be negative 1 plus 1, 2, 2, negative 1 plus 1, negative 2. And therefore, this is going to be assigned negative 0.125. 0.125 is equal to 111 and 2's complement. 110, negative 0.25. 101, negative 0.375. 100, negative 0.5. Together? Is that clear? Okay. Okay. Again, this is the code. Please, when you go home, try to run it. And one last thing to mention here. So we said the range of the input of the signal is between negative Fs and Fs. This is the range of the input signal. So in my example here that I created, I have the range between negative 0.5 to 0.5. What happens if the signal has a different range?
It's going to be clipped.
If you don't do anything, it's going to be clipped, yes.
Yeah.
But if I have a quantizer that works and expect a signal that is 1 volt peak to peak, and I want to quantize a signal, and the signal is 10 volt peak to peak, what do I do?
You increase your.
I can't if the quantizer is fixed. I have I'm given a quantizer. The quantizer, the input tells you the range is 1. You can input any signal between negative 0.5 and 0.5. However, I have a signal that is 5 plus 5 to negative 5, 10 volt peak to peak.
You could attenuate it?
You can scale it. Excellent. I can always take this signal that is, for instance, 5 volt to negative 5 volt divided by 10. Now the range of the signal is 0.5 to negative 0.5. Makes sense? Then I quantize it, and then I multiply it by 10 again. Is that clear? Makes sense? Okay. Any questions?
Is this bit depth? What is the name of this? It's like the levels of quantization, like the number,
The resolution.
resolution.
The resolution. I mean, depending on how many bits you use, will determine the resolution. The more bits I use, if I use 4 bits, here I have only 8 levels. If I use 4 bits, I'm going to have 16. 5 bits, 32. 2 to the power, the number of bits that I use.
So, like in audio, like they say it's like the variable bit rate, or there's a sampling rate, and then there's
The quantization levels.
I'm just trying to think of what they call that in audio, like on like your MP3 file or your AF, like they call it something, right?
I'm not sure what the one you're referring to. However, I mean, that's a good exercise if you like when you go
It's different, I think. Yeah.
when you go home, record an audio with MATLAB. Maybe we'll add it to the assignment. And then take the quantized levels and put them in bins and see how many bins you have. Then you will know how many bits you're using to quantize the signal. Does that make sense? Everybody? Okay. And I think in MATLAB, when you record a signal, you can specify, problem you don't have MATLAB to open it, but if you were to do a search on wave read or wave write, you'll be able to you'll be able to specify the number of bits that you want to use to quantize the signal. Okay.
So there's no equivalent of Nyquist theorem for that. You always lose data.
There is no equivalent to Nyquist, yes. You're going to always lose data. However, the more levels you use, the smaller the error. I mean, remember, the error is between delta over 2 and negative delta over 2. So the smaller the delta, the smaller the error. And of course, depending on the application, for instance, if it's an audio, you do experiments, you play the audio with this many levels, you tell people, can you tell the difference? And they tell you, no, we cannot tell the difference between 8 bits when it is using 8 bits or when it's using 10 bits. Then you realize 8 bits is enough for audio. Make sense? So depending on the application, that will determine how much error you can tolerate in the quantization process. Okay. With that, we are ready to move to the next topic that we're going to be covering, which is the Z-transform. How many of you are familiar with Z-transform?
I've heard of it.
Okay. Now this is a very important tool. And this tool will tie everything that we're learning together. And it is much simpler than the other transforms. Okay, so one of the transforms that we're familiar with is the Laplace transform. Imagine everybody familiar with Laplace transform. What is the Laplace transform of a signal?
Omega.
Anybody? About this. Integration of x of t e to negative st. Now what is the usage of the Laplace transform? The first thing is the Laplace transform encompasses the Fourier transform. What is the Fourier transform? It's equal x of t e to negative j omega t dt. So therefore, the Fourier transform is nothing other than x of s if I replace s with j omega, I will get the Fourier transform. So the Laplace transform encompasses the Fourier transform. The Laplace transform is also provides a solution, provides a tool to solving differential equations. What does the Laplace transform do? Why do we use it to solve differential equations?
You know, turns it from calculus to algebra.
Yeah, excellent. It converts the differential equation into an algebraic equation that can easily be solved. And we use the Laplace transform for continuous time filter design. Now the question that we're going to ask, is there a discrete time counterpart to the Laplace transform? Together? So we're going to see if we are dealing with discrete time signals, is there a tool similar to Laplace transform that we can be using? Okay, so what we're going to do is we're going to take our continuous time signal, we're going to multiply it by an impulse train. This is going to give me a sample signal, xs of t, which is equal to summation from negative infinity to infinity, x continuous of nt, delta of t minus n multiplied by t. Can everybody visualize what this signal looks like? Yeah, just impulses multiplied by the signal. So the impulses have different height depending on the signal. Now from this sample signal we can get x of n, the discrete time signal. Okay. So let's see what happens if we take the Laplace transform xs of s of the sample signal. So I'm going to take the Laplace of the summation from n equal negative infinity to infinity, x continuous of nt, delta of t minus n multiplied by t. So in order to get x of n, we sample the signal. Once we get the samples, we can generate x of n. So I came to this, I'm going to take the Laplace transform of this. What is the Laplace transform of this signal going to equal to? Anybody want to guess? This is a summation of deltas scaled by this amplitude. So therefore, I'm going to have that amplitude. I'm going to have a summation, apparently, from n equal negative infinity to infinity. I'm going to have this scaling the amplitude. And what is the Laplace transform of delta of t minus nt? Anybody want to guess?
Is it just NT?
Close. So if we plug in here with the definition, it's going to the Laplace of t minus nt minus n multiplied by t e to negative s multiplied by t dt. What is this equal to?
Is that shifting?
Yeah, it is. It's going to equal whatever this function at t equal to nt. So it's going to equal to e to negative n multiplied by t multiplied by s. Together? The integration of a delta multiplied by this is just going to equal this function at this point in time. Is that clear, everybody? So I have a function here, e to negative st. I'm multiplying it by a rect, if you like, that is at nt. What is the area going to be of the multiplication? This is going to get scaled by whatever the value of this function at nt. And therefore, it's going to equal e to nt multiplied by s. Okay. Now, if we define z as equal e to st, then I can write this as x of z equal the summation from n equal negative infinity to infinity, x of n multiplied by z to negative n. xc of nt is equal to x of n. And therefore, I can write this as x of z, the summation from negative infinity to infinity, x of n, z to negative n. And this is our z transform. Together? So we can see that the discrete time signal x of n, the z transform of the signal x of n, is identical to the corresponding sample signal xs of t. This and this are identical on it. So if I take the Laplace transform of the sample signal xs of t is the same as the z transform of the discrete time signal. Okay. So what are we going to use this z transform for? So as we're going to see, if I have a discrete time signal and I have a discrete time system, we're going to be using the Z transform to do analysis. We're going to be using the Z transform to do design. So both in the design of the system and the analysis of the system, we're going to be using the Z transform. So of the things we're going to be using in the analysis, if we are given x of n and the system model h of n, we're going to find, if I want to find the output, to find y of n, we can do any one of three things. We can do convolution to calculate the output, y of n equal to x of n convolve with h of n. I can use the difference equation. I can calculate y of n equal a y of n minus 1, a2, y of n minus 2, etc., etc. Or I can use the frequency domain. I can calculate e to j omega equal to x of e to j omega multiplied by h of e to j omega. Now we're going to see that the Z transform encompasses all these three methods. And similarly, when we are designing the system, if we are given x of n and desired y of n, what should the system be? So we can do any one of two things. We can do deconvolution or inverse filtering. We can do transformation from continuous time to discrete time. Or we can do frequency mapping. And as we will see, the Z transform also encompasses all of these methods. Okay. Is that clear, everybody? So we're going to be using the Z transform both to analyze any system and also to design the filters that we're going to be designing. So let's look at the Z transform and have an official definition of the Z transform.
Why do they call it Z?
Very good question. Because it's the subscript used in it, it's named after it. Does that make sense? So Laplace, we use S. The letter they chose for this was a Z. It became the Z transform. Does not have a name. Unlike the Laplace, they do not call it, well, some people might call it S transform, but it's known as Laplace transform. This one uses the Z, they call it Z transform. Okay. So the Z transform of a discrete time sequence x of n is an infinite series expansion about a complex variable z. Remember, z is equal e to st. S is complex, so z is also complex. Okay. So in this transform, we have x of n that goes to the x of z, and therefore x of z is equal to the z transform of x of n, and x of z, because this is capital letter in the z domain, is equal to the summation from n equal negative infinity to infinity x of n z to negative n. What is it? X of z exists for all values of z for which the infinite series converge. What is that? What is the analogy to Laplace transform? Remember Laplace transform, we have a region of convergence. Anybody? Region of convergence, Laplace transform. When you calculate Laplace, it exists for all the values of S that are in the region of convergence. So something similar, we have something similar here. So we have region of convergence. Which is the range of z for which x of z exists. Okay, so let's do some examples on the calculation of x of z. So if we are given x of n equal delta of n, what is the z transform of a delta of n? X of z is going to equal the summation from n equal negative infinity infinity delta of n z negative n. What is this summation going to equal to? One. Why not? 1 multiplied by z to 0, which is equal to a 1. So therefore, the z transform of a delta is just equal to a 1. What is the region of convergence? All z. There was no limit. This is always going to equal to 1, irrespective of the value of z. So therefore, the first entry in our table of z transform is that if I have a delta of n, it has a z transform that is equal to a 1, and the region of convergence is all z. Let's take another example. What happens if I shift this x of n So I have x of n delta of n minus 4 and multiplied it by 3. What is x of z going to equal to? Summation, negative infinity to infinity, 3 delta of n minus 4, z to negative n. What is this going to equal to? Excellent. 3 times z to the negative 4, which is a 3 over z to the power of 4. What is the region of convergence? What values of z we cannot have? 0. All z except z equal to 0. Because if z is equal to 0, this is infinity. It means that we did not converge. So therefore, if I have a delta of n minus b is going to have a z transform that is going to equal to a z to negative b. And it is all z except z equal to 0. Okay, let's take another sequence or another example. If we have x of n equal to 1/2 to the power of n multiplied by u of n. What does this look like, this signal? Something like this. At 0, it's a 1/2, 1/4, etc. What is x of z? X of z, the definition, summation from n equal negative infinity to infinity, 1/2 to the n, u of n, z to negative n. What is this going to equal to? We can start from 0 because I have u of n. What is u of n?
Step function.
Step function. So it starts from 0, so I can just start from n equal to 0 to infinity, 1/2. I can write this 1/2 multiplied by z to negative 1 and all to n. And this summation is going to equal to 1 over 1 minus 1/2 multiplied by z to negative 1. I'll probably bring next time a summary of formulas that will help us when we calculate these summations. I thought I had them here. But if we have a summation from n equal n1 to n2, a to the power n, this is equal a to n1 minus a to n2 plus 1 divided by 1 minus a. Okay. Okay, what is the region of convergence? how do we determine the region of convergence? This summation will only converge, as you can see from here, if this is less than 1, isn't it? Because we're taking it to the power n. If this is bigger than 1, it's going to be, if it is, for instance, 2, it's going to be 2 to 0, plus 2 to 1, 2 to 2 squared, 2 cubed, it's going to go to infinity. However, if this is less than 1, then as n increases, what's going to happen to this summation? It's going to get smaller and smaller and smaller. Make sense, everybody? So therefore, the condition to have this converge, we need to have the magnitude of 1/2 z to negative 1 to be less than 1. The magnitude of this in the summation has to be less than 1. And that is the same as saying we want the magnitude of z to be greater than 1/2. This is the same as saying 1/2 multiplied by 1 over z less than 1, and therefore the magnitude of z has to be greater than 1/2. Okay. So therefore, we have the region of convergence and we have the z transform. We can have another entry which says that if I have an alpha to the power of n multiplied by u of n, is going to have a z transform, that is z over z. Oh, let me go back here. Now we can simplify this. We can multiply the numerator and denominator by z, so it's going to become z minus 1/2. So in general, if I have 1/2, it's going to be z over z minus 1/2. If I have alpha, it's going to be z over z minus alpha. Okay. So therefore, we can write this as z minus alpha, and the region of convergence is z greater than the magnitude of alpha. Okay. So this is another entry. Another example, if we have x2 of n equal to negative 1/2 to the n u of negative n minus 1. How does this signal look? The signal starts when n is negative. So when n is 0, it does not have a value. When n is equal to negative 1,
How can the samples be negatively indexed?
why not? What's the objection?
I thought they were always greater than 0.
If there is u of n, it's greater than 0. U of n starts at 0 and n greater than 0. U of negative n minus 1, where does this start?
Starts at negative 1.
It starts at negative 1 and goes to negative infinity. Does that make sense? U of negative n minus 1.
For certain functions, you can have it where it exists before at time equals 0. If you want it to be a little
This is going to start at negative 1 and it goes all the way to infinity. Does that make sense?
So we're not in the sample domain?
We are in the sample domain. What's the confusion? I mean, so far, the signals, you're right, the signals we've seen
I've always been positive. Because it's an index of a...
we always looked at the positive
Sure.
index of the signal. So when I have a signal, for instance, and I say n equal, this is 0, 1, 2, 3, 1, 2, 3, this is sample, sample, sample. I have samples here.
Okay.
Does that make sense? No, you should know. It has to make sense. We're going to be agnostic to the time. Negative time, positive time does not bother us.
All right.
Now, if you like, I mean, think of this as a file. You have all these values, and you choose the index of 0 at wherever you want it to be.
Okay.
Does that make sense?
Sure.
I mean, the time is relevant. So I can shift the time and say, oh, this is all time positive. Or I can say, okay, this is my reference time. Any samples that I took yesterday are negative samples. Anything I'm taking now is 0. I'm going to take from now, it's going to be positive index. Make sense? But all the discussion that we had will apply to the case where the sampling goes from negative infinity to infinity. Make sense? And if you go back to all the formulas of the sampling, it was always the summation from negative infinity to infinity. So n was always from negative infinity to infinity. Sounds good? Okay, we'll stop here. We'll finish this on Wednesday. Any questions?